Welcome to The Explainer. I am so glad you're here with us today. We're diving into a topic that honestly completely bends our everyday logic: quantum computing. We're going to look at how the absolute tiniest building blocks of our universe are fundamentally tearing up the rulebook on computers, data, and, well, reality itself. But we're going way beyond just the hardware today. We're looking at what this actually means for our own human understanding of truth and certainty. Let's get right into it. You know that incredibly frustrating feeling when you can't find something that's literally right under your nose? You're frantically tearing the house apart looking for your glasses, narrowing your focus only to realize they're resting right on top of your head. It's a hilarious little quirk of human nature, right? But it actually sparks a pretty provocative mental model. What if the very act of looking really closely at something actually obscures it? What if, when we zoom all the way in to find absolute certainty, the universe just kind of refuses to be pinned down?
Which brings us to this wonderful piece of wisdom, a Papa's take, if you will. Papa, the author of the newsletter guiding our explainer today, often channels the profound insights of his late father, Papa Q-Bear, and his spouse, Colonel Debs. They shared this guiding philosophy that perfectly mirrors the quantum world. They'd say, sometimes the closer you look at something right under your nose, the more the goalpost moves when you say, aha. And as you'll see, this isn't just a quirky family saying. It's an undeniable, mathematically proven law of the universe.
Part 1. The context. The illusion of certainty. To really wrap our heads around this quantum revolution, we first need to look at the predictable rules of classical physics. This is the comfortable, everyday world we're used to, governed by rules we can see, from throwing a baseball to using the smartphone in your pocket. Think of our classical reality like a super high-resolution digital image. When you're looking at it from a normal distance, everything is perfectly sharp, defined, and certain. And our current computers operate in this exact realm of absolute certainty using bits. Those are tiny switches that are definitively either a 0 or a 1, off or on. But if you zoom into that digital photo far enough, those sharp edges completely disappear and you're just left with wobbly, fuzzy pixels. At the subatomic level, the realm of electrons and photons, nature gets incredibly fuzzy just like that. Down there, information is processed using qubits. So instead of being a strict 0 or 1, a qubit exists as this fluid wave of probability. It's literally an entirely different language of reality. Moving right along to part 2, the tension, the quantum computing landscape. Now that fundamental fuzziness creates some massive tension in modern science. It's actually launched us into what experts call the NISQ era. That stands for the Noisy Intermediate Scale Quantum Era. We're actively trying to build machines that can harness this wild, unpredictable, microscopic world. So how on earth are scientists taming these fuzzy probabilities to build supercomputers? Well, they're tapping into some truly mind-bending behaviors. The first one is superposition. If you imagine a classical bit as a person standing on a ladder, they can be on the bottom rung, state 0, or the top rung, state 1. It makes zero sense to say a person is standing on the top and bottom rungs at the exact same time. But a qubit? A qubit can do exactly that. A great way to visualize this is to think of a musical instrument, like a snare drum. When you strike that drum, it doesn't just vibrate on one single isolated tone. The physical tension allows it to hold multiple frequencies, or states, all at the exact same time. Qubits vibrate in this state of multiple possibilities too, which allows a quantum computer to explore millions of potential answers simultaneously, instead of just one at a time. It's a total game changer. And that brilliantly sets us up for our next concept, which is entanglement. Albert Einstein famously called this spooky action at a distance, and you'll see why. Imagine you have 2 coins. You keep one and you give the other to a friend who travels all the way to the moon. You flip your coin right here on Earth, and it lands on heads. Instantly, literally faster than the speed of light, your friend's coin on the moon will also land on heads. The 2 qubits are inextricably linked in this beautifully coordinated dance. Their fates are completely bound together. This spooky connection allows quantum computers to process correlated information with a speed and complexity that our ordinary computers just cannot even dream of matching. But here's the catch. This fundamental fuzziness places an absolute hard limit on our ability to know things. This brings us to the Heisenberg uncertainty principle, established way back in 1927. It essentially states that the universe is fundamentally blurry at its core. If you measure an electron to find its exact position, you disturb it so much that you completely lose all knowledge of its speed or momentum. Think of it like this. If you bounce light off a massive skyscraper to see it, the building obviously doesn't move. But if you bounce a tiny photon of light off an electron to see it, the physical impact violently knocks that electron completely off its course. The very act of observing the thing actually changes this reality. Crazy, right? Yet, despite this deep, inherent uncertainty, our technological progress has been absolutely staggering. From Werner Heisenberg defining the limits of certainty in 1927 to Richard Feynman proposing quantum computers in the 1980s, things have moved incredibly fast. In 2019, Google actually claimed quantum supremacy by running a calculation a classical computer practically couldn't finish. And today, we are deep into that NISQ era, with companies like IBM releasing massive 433-qubit processors like their Osprey chip. Now, the hardware is still noisy and pretty error-prone because those qubits are so incredibly fragile, but the landscape is evolving at breakneck speed. You might be wondering, why go through all this trouble just to try and control such fragile, uncertain little particles? Well, because the payoff is going to be monumental. By using things like superposition and entanglement, quantum computers will soon solve massive optimization problems that would completely overwhelm our classical machines. We're talking about instantly routing complex global supply chains for absolute peak efficiency. In medicine, they'll be able to perfectly simulate molecular behavior to design life-saving pharmaceuticals from scratch. And in data security, they are going to completely rewrite the rules of cryptography, giving us networks that are protected by the literal laws of physics. Okay, let's move into part 3, the connection, the moving goalpost. Let's connect this all back to our daily lives. We've talked about qubits, entanglement, and these massive superprocessors. But at the absolute center of all this technology is that Heisenberg uncertainty principle. And honestly, it's not just an engineering hurdle. It's a profound philosophical shift in how we view discovery and truth. The fact that measuring an electron fundamentally disturbs its momentum tells us something incredible about life itself. Pinning down an absolute truth often obscures the bigger picture. Just like looking too hard for your keys can make you totally blind to the fact that they're sitting right on top of your head, hyper-focusing on one precise detail in our lives can cause us to lose our broader perspective. The act of observation fundamentally changes the outcome. It turns out the universe just fiercely resists being put into a perfectly tidy, certain little box. Which brings us to our final section, part 4, the synthesis, embracing the unknown. As we synthesize all this incredible data from the Department of Energy, NIST, and leading tech pioneers, we really have to recognize that quantum computing isn't just about raw computational speed. It is a masterclass in embracing the unknown. Let's quickly summarize the clear takeaways we've covered today. Number 1, qubits replace absolute certainty of classical ones and zeros with fluid, wavy probabilities. Number 2, phenomena like entanglement and superposition allow these machines to explore millions of solutions simultaneously. Number 3, we are right in the thick of the noisy intermediate-scale quantum era. The tech is incredibly powerful, but still super delicate and prone to errors from outside interference. And finally, number 4, once we conquer those errors, this technology is going to utterly transform global logistics, medical drug discovery, and digital security. So the absolutely crucial point here is this. Quantum mechanics brings us a whole new perspective on the inability to find something right under your nose when you're looking for it. As Papa Q Bear and Colonel Debs instinctively understood, the universe is built on a foundation of shifting possibilities. The uncertainty is literally rooted in the Heisenberg uncertainty principle. Are we really certain that when we discover something, it is the final answer? Or, thanks to the very nature of our universe, has the goalpost already moved the exact moment we say, aha? It's a beautiful, humbling thought to carry with you. Thank you so much for joining me on this explainer. Keep your eyes open and don't forget to embrace the uncertainty.